Okay, very good afternoon all. Welcome back to online training on GATE 2021 organized by Electronics and Communication Engineering Department, VVCE Mysore. I am Jayanna SS, working as an assistant professor in the Department of ECE, VVCE Mysore. Okay, for the next 1.5 hours, I am going to discuss on the topic digital circuits related to GATE 2021. Okay, let us see the syllabus of they are divided into 6 subtopics. Okay, they are divided into 6 subtopics. Okay, the first one is number representations and combinational circuits, sequential circuits, data converters, semiconductor memories, and computer organizations. Okay, let us see the weightage analysis of digital circuits in previous years. Whereas in 2015, okay, in 2015 paper 1, in 2015 paper 1, it is asked for 9 marks, and paper 2 is also for 9 marks. Paper 3 in 2015 it is also asked for 9 marks. Coming to 2016, it is asked around 8 to 10 marks. Okay. Coming to 2017, it is asked for 11 marks. 2018, 11 marks. 2019, 9 marks, and 2020, 9 marks. On an average, okay, on an average it will be 9.5. Okay, you can expect around 6 to 10 marks in 2021. Okay, fine. These are the important topics which they have asked repeatedly. They are definitely going to ask questions on finite state. They are going to ask on counters, excitation tables, finite state machines, K-map, analysis of K-map by using SOP and POS, multiplexer. They are going to ask on the MOS transistors and PLA. These are the general or important topics you need to learn in order to crack the gate. Okay, fine. Now, next, moving further, these are the contents what I am going to explain. Okay, first I am going to explain what I mean by combinational circuits, and I am going to solve few problems on that. In combinational circuit, I am going to deal with Boolean algebra, minimization of functions using Boolean identities and K-map method. How we are going to solve the given expression by using K-map. Okay, then I'm going to deal with multiplexer decoder. Okay, fine. Next, moving further, I also deal with sequential circuits. Okay, in sequential circuits, I'm going to solve few problems, gate-related problems on flip-flops, counters, and shift registers, and finite state machine. Okay, these are the concepts I will going to cover in this session. Okay, next. Coming to Boolean algebra, you must know what I mean by Boolean algebra, where you are going to represent the variable in the form of zeros and ones, or you can say that true or false. Where it is known as Boolean algebra. It is a section or part of algebra. Okay, fine. Next, in that you are going to you must know about these are the pre-requirements or prerequisites you must know in order to solve few problems on digital circuits. Okay, these are the properties of Boolean functions. They are you must know about commutative property, associative, distributive. Next, rules of Boolean algebra, like what is the 1 plus 0, what is a plus a bar, and what is a dot a bar, and you must know what do you mean by a dot 0. Okay, these are the rules. Next, there are some theorems where what happens if a plus a bar b equal to what, a plus b whole bar equal to what. This is De Morgan's theorem. These are the pre-requirements you must know. Okay, it's a easy topic. You can definitely score 1 to 2 marks in this Boolean algebra. Okay, fine. After that, based on what you have learned here, you are going to apply that one, and you are going to simplify the expression. This is known as simplifications of the given expression. Okay, that expression what you are going to get can be classified as sum of products. I'm going to classify that one sum of products as I mentioned here, and product of sum. Okay, you can call this one the sum of products and products of sum. Okay, what is the major difference between sum of products? Means where this is a representation of sum of products. This is a representation of sum of products. Okay, where you can see that, okay, it is a summation, or it is the summation of products. It is a summation of products. Okay. Okay. Suppose if I consider POS, I need to write this one as A bar plus B. This is the first term. A bar plus B plus C. Okay. Into A bar plus B plus C. Okay, these are, I have taken the two max terms. These are known as max terms. Here, these are known as mean terms. Okay, I'm going to classify this one as mean terms. Okay, it is known as sum of products. There are three mean terms. You can see that there is a product here and there is a summation here, sum here. So it is known as sum of. It is a sum of products. Okay, fine. This SOP can be classified as canonical or standard SOP and minimal SOP form. Coming to canonical SOP, you can see that suppose here y will be the output. It will be the dependent variable. I can say this, y is a dependent variable. Okay, where A and B, C will be the independent variable, where dependent variable y is dependent on the input A, B, C. Okay, here you can see that in the canonical form or standard SOP form, you can see all the variables in it. You can see that you just look into the first variable A, B bar, C bar, where there is three variables. Okay, it may be a normal form or it may be a complemented form, but it should contains all the variables which are included, which is the output is dependent. Okay, here coming to here A, B bar, C, A, B, C. Whereas minimal SOP form, it is the simplified version of this canonical form, where it does not contain all the terms, all the input terms in the expression. It is known as minimal SOP form. Okay, this is about SOP. This is not about sum of products. Similar to this one, we have product of sum. As I told in the mean terms. Okay, here it is similar to SOP. It will be product of sums. Okay, it will be a product of sums, where it consists of the product, where it comprises of product of sums. You can see that it comprises of product of sums. Again, it can be classified as canonical and minimal POS form. Okay, as you can see, all the variables are present here in the canonical POS form, where in the minimal POS form, it does not contain all the variables, whether it may be a complemented form or in the normal form. So it is known as minimal POS form. Okay, whereas minimal POS form is the simplified version of the canonical POS form. Okay, fine. Let us move further. Coming to combinational circuit, these are the basic introduction which I am giving now. Okay, coming to combinational circuit, you know that the combinational circuit, the output, the current output, if you consider a circuit or if you consider a system, or if you consider a circuit, the current output, the present output depends on the present input. The present output only depends on the present input. Okay, it is known as combinational circuit. Okay, this is the actual definition of combinational circuit, where it can be classified as arithmetic or logical functions, data transmissions, and code converters. In the GATE syllabus, you do have all these concepts. Okay, fine. Whereas in arithmetic and logical functions, it comprises of adders, subtractors, comparators, PLD, that means programmable logic devices, and then coming to here, data transmission, multiplexer, demultiplexers, encoders, decoders, and in code converters, you do have binary, BCD code, and 7-segment. How we are going to convert the analog data? Suppose if I am going to give 5 volts, how we are going to convert into a 7-segment? How we are going to get the output in the 7-segment display? Okay, these are the things you are going to learn. These are the things you have in the GATE 2021 syllabus of digital circuits. Okay, fine. Let us understand by solving few examples. I have taken some of the questions from the GATE, and I'm trying to solve that one. Let's try to solve that one. Okay, this is one of the questions which is asked in the GATE. Okay, that is, you need to match the logic gates. the column. This is the first question. We need to match the logic gates in the column A with the rest with their equivalent in column B. Okay, fine. So first, what I'm going to do is, this is my column A. I need to match that with the column B. So what I'm going to do here is, first for consideration, I'm going to take some inputs. I'm going to take A and B will be the input to the first gate. Okay, fine. The output will be, as you know, it is a NOR gate. As you know, it will be a NOR gate. So you are going to get A plus B whole bar. You will get A plus B whole bar. You can write this one as A bar dot B bar. You can write that one as A bar dot B bar. Here, coming to this one, I'm going to take A, B here. I'm going to get A dot B bar. So the expression will be A bar plus B bar. Coming to here, A, B. Okay, here it is XOR, right? I can write this one as AB bar plus A bar B. Okay, coming to here, this is XNOR. So I'm going to write this one as AB plus A bar B bar. Okay, next, after that, coming to this column, I'm going to take another color in order to represent that one. So I'm going to take green. Okay, fine. So this one will be, again, I'm going to call this one as A and this one is B. Since it is a XOR gate, since there is a bubble here, you can see the bubble here, it will be barred here, it will be barred, it will be inverted here. So what I'm going to get here is A, B double bar, so plus A bar, B bar, which can be written as AB plus, sorry, A, B bar plus, sorry, I'm not getting, there is no bar here, AB A bar, B bar. Okay, fine. Next, after that, I'm going to apply A and B here. The output will be barred here. I'm going to get A bar plus B bar. Next, coming to here, I'm applying A and B here. So here it will be A bar. So since it is a XNOR, I'm going to get A, since A bar B, since it is barred here, I'm going to write A bar B plus A double bar B bar. So what I'm going to get here is, which is equal to A bar B plus A B bar. Coming to the last one, I'm taking input as A and B here. The output here is A bar, and here also, since it is a bubble here, it will be B bar. I'm going to get A bar, please handed right, A bar dot B bar. Next, I'm going to try the mapping of this one. So you can see that this P, this combination P, this shows that it is equal to 4, right? This P equal to 4. This is, since you are going to get A bar, B bar, it is equal to this one. Next, coming to A bar plus B, look at here. This Q is equal to 2. This expression is equal to the two expressions. Coming to R, AB bar plus A bar B. So it is equal to 3. Next, this one, fifth one, AB plus A bar B bar. So it will be equal to 1. Okay. In the option, they are going to give whether Q equal to 1, Q equal to 2, Q is R equal to 3, S equal to 4, so on. So you are going to select that this Q should be, this P is equal, the equation of P is equal to 4, and Q is equal to 2, and R is equal to 3, and S is equal to 1. Okay, this is the combination you are going to select. Okay, fine. Next, moving to second problem. They are given that for the output F to be 1 in the logic circuit shown, the input combination should be. They are given that the F is equal to 1. They are given that F is equal to. They are given that the F is equal to 1. They're given that f is equal to 1. You need to select what is the, if you want to get f is equal to 1, what are the inputs? What are the inputs A, B, and C? Okay. First, you know that this is the XOR gate, and you know that this one is XNOR gate, and this one is XNOR gate. Okay. Since I am giving A and B as the input, I'm going to write this one as A XOR B. A XOR B is the first gate output. So coming to here, okay, coming to the next one is A XNOR B. A XNOR B is the another output of this XNOR gate. Output of this XNOR gate. Coming to this one, the C is XNOR with the another, right? So I'm going to write this one as XNOR. This is XOR. This is XNOR. This is the finalized expression for F. Okay, this is the finalized expression for F. Okay, but we know that A XOR B, which is equal to A XOR B complement. We know that A XOR B equal to A XOR B complement. So what I'm going to write here is, so I'm going to consider only this expression. I'm going to consider a part of the expression, that is A XOR B. Okay, dot I'm going to write this one as A XOR with a complement. So I'm going to get the same expression. So if I take X is equal to A XOR B, if I take X is equal to A XOR B, I'm going to get X XNOR with X bar, X XNOR with X bar. If I'm going to write that one, I'm going to get that X bar plus X bar plus X bar into X double bar. This double bar get cancels. I'm going to get X bar plus X bar. Okay, if I take X is equal to 0, obviously this X bar equal to 1. If I take X is equal to 1, obviously X bar is equal to 0. I'm going to get the answer equal to 0. So I know that this expression whole is equal to 0. So I'm going to get 0. This is XNOR with 0, XNOR with C. Okay, 0 should be XNOR with C. Next, what I'm going to do here is, I know that the expression is given by 0 into C. We know that A XNOR is 0 into C plus 0 bar into C bar. You know that 0 into C is always equal to 0, which is equal to 0 bar into C bar. What is 0 bar? 0 bar equal to 1. 1 into C bar. You are going to get C bar. Okay. If you are going to get 1 C bar. If you are going to get C bar. Okay. Next, what you are going to do here is, so you know that the output of this XNOR, it should be 1. This F should be equal to 1. This F should be equal to 1. Okay. In order to become this F should be 1, okay, you need to select this C bar. You need to select this C bar. If C bar equal to 1, okay, first select C bar equal to 1. Okay, if you put C bar equal to, if you take C bar equal to 1, obviously this C is equal to 0. Okay. If you take C bar equal to 1, this C equal to 0. C equal to 0. If you put C is equal to 0 here, if you put C is equal to 0 here, you know that 0 XNOR with 0, you are going to get 1. 0 XNOR with 0, you are going to get 1. That means you must put C is equal to 0. Suppose if you put C is equal to 1, therefore the C bar equal to 0. If you put C equal to 1 here, 0 XNOR with 0, 0 XNOR with 1, you are going to get 1. Okay, 0 XNOR with 1, you are going to get 0. It is not satisfying. This F is equal to 1. So that C should be equal to 0. In all the options, the C is equal to 1. Okay, here the C is equal to 0. You can check for A equal to 1, B equal to 1. This option will be the correct option for this question. Okay, this is a simple method. Try to understand this one. You can solve this one within 1 minute. Okay. I explained in detail, that's it. Okay, so it took a lot of time. Okay, fine. Let us move to third question. That is canonical SOP of AB plus BC bar. Okay, first they are given that you need to write the canonical form of this expression. Okay, for that, first you are going to write the actual equation AB plus BC bar. Next, in order to, this is the minimal SOP, you need to write the canonical SOP. In order to write the canonical SOP, what you are going to do is just take, okay, just add C plus C bar, missing terms there. Here the C is missing. Just add C plus C bar. Just multiply C plus C bar to that equation. Here, compare here, coming to here A is missing, right? What you are going to do, just multiply A plus A bar here, and you are going to get BC here, sorry, BC bar. So the expression will be ABC plus ABC bar plus ABC bar plus A bar BC bar. So you can see that there are two terms, ABC bar, which is equal to ABC bar, ABC bar plus ABC bar. Suppose if you have A plus A, you are going to write this one as A. Similarly, ABC bar plus ABC bar can be written as single ABC bar plus ABC plus A bar BC bar. Okay, just check which expression matches this one. Okay, if this is ABC bar, A bar BC bar. Okay, this is the one way of approaching this question. Another way is just change the values of, just apply the values of A equal to 0, B equal to 0, and C is equal to 0 in the expression, and check the individual equation. Okay, if the given equation is too much, it consists of too much summation or sum. So what you are going to do, just change the values of A equal to 0, B is equal to 0, and C is equal to 0, and put the equation, which equation satisfies, that one will be the correct answer. Okay, this is another way of approaching to this question. Okay, fine. Moving to the next question, this is the fourth question. The Boolean function, they are given the Boolean function that this is, you know, that this pi of 3, 4, 6, 7, 11, 12, 13, 14 and 15 is equivalent to, this is the POS expression. They are given the POS expression. Okay, you need to write the 4 variable K map since it has 4 variables. Okay, what I am going to do, this will be the AB and this one will be the CD. Okay, I am going to apply the 4 variable K map. For understanding purpose, I am going a bit slow. Okay, 0, 0, 0, 1, and this one will be 1, 1 and 1, 0, 0, 0, 0, 1, 1, 1 and 1, 0. We are going to write this one as 0, 1, 2, 3, this one will be 4, 5, 6, 7, this one will be 8, 9, 10, 11, 12, 13, this one will be 14, and this one will be 15. Okay, fine. Next, okay, they are given that 3, 4, 6, 7 are zeros. 3, 4, 3, I am going to write 0 here. 4, this one will be 0. 6, it will be 0. 7, 0. 11 will be 0. 12 will be 0. Next 13 will be 0. 14 will be 0. And 15 will be 0. Just I am going to map this one. I am going to look for 2 power. First, I am going to look for 2 power 4 because since it has it has 4 variables. So there is I'm going to say 2 power 4, 16. Can I make that one? 2 cube, I'm going to look for that one. There is no 8 zeros here. Okay, 8 successive zeros there. Then 2 square, there are 2 squares. There is 4 successive zeros. What I'm going to do, I'm going to map that one. Okay, what I'm going to do here is, okay, I'm going to map this one. Okay, this is the first one. And this one will be the second. I'm going to call this one as second. I'm going to call this one as third. Okay, if these are the essential prime implicants. These are known as essential prime implicants. These 3 what I have mapped is essential prime implicants. So I need to write the SOP form. I need to write the POS form. So for that one, I'm going to write this one as, first I'm going to write this one. That is A. Since I need to write in place of, there is 1 here, I need to write A bar plus B bar. A bar plus B bar will be the expression for this one. So I'm going to call this one as Q1. Coming to this one, coming to Q2, you can see that these 2 are common. Okay, into here there is B1. There I'm going to write B bar plus, I'm going to look here. This one is common. I'm going to write D. Okay, since it is 0 here. There's in POS 0 is represented as, suppose if I take A, the variable A, 0 is represented as A and 1 is represented as A bar in POS. So next, this one is second one. Coming to this one, Q3. you can see that C, D, as I told, C is represented C bar and this one is represented D bar. So into C bar plus D bar. Okay, I'm going to look this one. So you can see that A bar, you can see the option number D, that is A bar plus D bar, C bar plus D bar, and B bar plus B. Okay, this will be the expression for that one. So moving further, move to another problem. Okay, the Boolean function, they are given the SOP expression with don't care conditions. Okay, they have asked the equivalent equations. So you need to apply the K-map and you need to identify which expression. They are given the minimal SOP expression. They are given the minimal SOP expression. So what you are going to do, since it is a 4 variable, you are going to apply 4 variable K-map. Just draw the 4 variable K-map. I'm going to call this one as A, B, and this one as CD. 0, 0, 0, 1, 1, 1, 1, 0, 0, 0. Okay, next you can see that there is a 0 here. 0 will be don't care. 0 is the don't care. Next 1 is 1. 2 will be the don't care. So 2 will be don't care. 3 is 1. Next 4 is 0. I'm leaving as it is. Next 5 is don't care. 5 is don't care. 7 will be 1. 7 will be 1. Then 11 will be 1 and 15 will be 1. So I am going to map this one. Okay. I'm going to map this one. So this will be the quad, first quad, and this will be the second quad. Okay, I'm going to write the SOP expression for this one. This is SOP expressions. I am going to write A bar, B bar plus this is, I have written for this one. I'm going to write for this one C, D. So I'm going to just look into this one. So A bar, you can see option number C, A bar, B bar plus CD. Okay, this option C will be the correct one. Okay, fine. Moving further, the SOP expression for, you need to write the SOP expression for this one, F is equal to AB plus CD. Okay, is equivalent to the POS expression. They are given the SOP expression. You need to write the equivalent POS expression. Okay, first they are given. We know that for understanding purpose, we know that A plus B into A plus C can be written as A plus BC. Or if they are given A plus BC, we can write this one as A plus B into A plus C. Let us prove that one. If they think that they are given A plus BC, we are going to write this one as A plus B into A plus C. Just multiply this one with this one. So you are going to get A into A plus A into B plus A into C plus B into C. Okay, B into C. You can take from this one, you are going to take A common. So you are going to write here A into A will be, which leads to A here. If you take A common, you are going to get 1 plus B plus C plus BC. As you can see that 1 plus B, irrespective of these variables, it will be 1. So you are going to write this one as A plus BC will be the actual, which is proven. That is A plus, we can write A plus BC as A plus B into A plus C. Okay. Similarly, okay, they are given that AB plus CD. What I am going to write? So this is the SOP expression. Since I need to write the POS expression for that one, so what I am going to do is I am going to write AB plus C into AB plus D. I applied this theorem, this property. I applied this theorem. Okay. Next, what I'm going to do, next again I'm going to apply the theorem. So I can write this one as A plus C into B plus C. Next, A plus D into B plus D. Okay, this is the I'm getting all the POS expression, all the POS. You can see that this is the product of some expression. Just I'm going to look in the given option whether this option is present in the given options. So for that, A plus C I'm getting this one, B plus C I'm getting here, A plus D I'm getting here, and B plus D I'm getting here. This option B will be the correct option for this question. Okay, fine. Next. The next question is, they are given this expression f of a, so this is a POS expression. They are given the POS expression f of a comma b comma c equal to max terms of 2 comma, that is pi of 2 comma 3 comma 6. Okay, you need to realize this expression for two input gates. What is the minimum number of gates? Two input gates are of same type, or of not different type, or of same type required for implementing this expression. They are given that one. So for that, in order to reduce that one, so I'm going to apply a K-map. Since it has three variables, I'm going to apply three variable K-map. So for that, I'm going to take A here. This one will be DC. We'll call this one as 0. This one has 1, 0, 0, 0, 1, 1, 1, and 1, 0. This one 0, 1, 2, 3, 4, 5, 6, and 7. Next, I'm going to apply here. This is since this is the max terms. 2, 3, 6. 2 will be 0. 3 will be 0. And 6 will be 0. Next, I'm going to map this one. So if I'm going to map this one, I'm going to get this expression. Okay, if these are zeros, means the remaining terms will be 1 here. Since my focus is on this POS, I'm not focusing on that one. Okay. Okay, I'm going to write the expression for this one first. So I'm going to get that one as A. Since this is since 0 is represented as A here, A plus the common is B bar, since 1 is represented A plus B bar. So I'm going to write this one. So here is B bar plus C. Okay, if you take this expression, in order to realize this one, you need, and they have given that note both the normal inputs and their complements are available. This is the another thing they have given that. So you can take A as an input, or you can take A bar as a input. Both normal inputs and their complements are available in this circuit. So, okay, that is the one thing they have given. Another thing they have given. Okay, here A plus B bar. Here you need OR gate, and here you need AND gate. Here OR gate, here AND gate. But they ask that same type required. Two inputs are of same type required for implementing the Boolean function of this one. Okay, so let us convert this to a NAND and NOR, because since NAND and NOR are universal gates, NAND and NOR gate are universal gates, we're going to get a single gate, right? Let us try to solve by using that one. What I'm going to do is, B bar. So I'm going to take B bar common. I'm going to get B bar plus, I'm writing as is, B bar plus AC. Okay. Since this is a SOP expression, the expression for NAND gate will be A into B bar. I'm going to take a double bar here. A bar plus AC whole bar. Okay. I'm going to apply the first complement here by applying Morgan's theorem. I'm going to get A bar, A double bar, dot, A double bar, dot, AC bar, whole bar. So the bar get cancelled. The input will be the B in AC bar. In order to realize this one, AC bar, in order to realize A will be the input to the one NAND gate and C will be the input to the another NAND gate. I need one NAND gate, okay, and B I'm going to give as it is. Then B and output of this gate is given to the another NAND gate. I'm going to NAND that one. I'm going to get another. I need another NAND gate in order to NAND that one. So the required number of so I need two NAND gate in order to implement this expression. So the minimum expression will be 2. The minimum number of two input gates will be 2. Okay, I'm going to write this one as 2. This is a numerical problem which is appeared in the previous gate exam. Okay, fine. Moving further, they are given that the 3 to 8 decoder is used to implement the function f. The expression for f is, okay, they asked the final expression f. Okay. So you can directly say that here, if there is if you are going to do 0, 0, 0 here, you are going to get 0 here. Because it is an active low output. You have active low outputs. Here you are going to get 0 here, 0 here, 0 here, 0 here. So what you are going to do here is, you know that since how we are going to write this one, since there is A, B, C as the input. So first one you are going to write this one as A bar, B bar, C bar as it is. A bar, B bar, C bar. How we are going to represent 0? How we are going to, this is 2, right? How we are going to represent 2? How we are going to represent that 2? So it is ANDed. It is ANDed. So I am going to write in the multiple form. Okay? It is NANDed, sorry. It is NANDed. Next here, 2. How we are going to write 2 here? How we are going to write this one as A bar, B, A bar, B bar, C. Next coming to 3. 3 is written as A bar, B, C. Okay. Next coming to here, 7. 7 is written as A, B, C. Okay, fine. A, B, C. I'm going to get A bar, B bar, C bar plus A bar, B, C bar. So complement get cancels, complement get cancels plus A bar, B, C, A bar, B, C, complement get cancels plus ಇದು ವರ್ಕ್ ಆಗ್ತಿಲ್ಲ ತಗೊಳ್ಳಿ ನಾ ಅವಾಗಲೇ ಸೌಂಡ್ ಬಂತು ಕಡೆ ಇದೆ ಮತ್ತೆ ಇಂಟರ್ನೆಟ್ ಕನೆಕ್ಷನ್ ಹೋಗಿತ್ತು ಓಕೆ ಓಕೆ ಚೆನ್ನಾಗಿ ಬರ್ತಿದೆಯಾ ಸರ್ ಸರಿ ಆಯ್ತು ಚೆನ್ನಾಗಿ ಬರ್ತಿದ್ದೀರಾ ನಿಜ ಹೇಳಿ ಸರ್ ಇದು ಪ್ರೀವಿಯಸ್ಸಾ? ಓ ಸರ್ ಇದು ಭಾಳ ಕಷ್ಟ ಇದೆ ಎಕ್ಸ್ಪ್ಲೇನ್ ಮತ್ತೆ ನೆಕ್ಸ್ಟ್ ಹೋಗ್ತೀನಿ. Okay, sorry for the disturbance. There is a technical problem over here. Okay, fine. Moving further, I'm going to erase this stuff. Okay. Here you can see that okay. Here you can see that this one is 0. It is a active low. This one is active low. This one is active low. Okay, fine. Here it is an active low. Here it is active low. What I'm going to do here is, suppose if there is no bubble here, think that if there is no bubble here, how we are going to write the expression A bar, B bar, C bar. Think that there is no bubble here, how we are going to write the expression A bar, B, C bar. Similarly, we are going to write for 3 and similarly we are going to write for 7. Next, what you are going to do here, there is a bubble here. So what you are going to take, you are going to take the not operation of that one, since for that combination you are going to get 0 here, the remaining bits will be 1 here, the remaining which is not connected will be 1 here. Okay, next it is NANDed, so I'm going to take whole complement here. If I apply De Morgan's theorem here, I'm going to get A bar, B bar, C bar plus A bar, B, C bar plus A bar, B, C plus A, B, C. This is the SOP expression. This is the SOP expression. In order to write in terms of mean terms, so what is this A bar, B bar, C bar? A bar, B bar, C bar will be 0. A bar, B will be A bar, B, C bar will be 2. A bar, B, C will be 3, and A, B, C will be 7. Suppose in exam you can expect there is no bubble here. If they are connected with an AND gate, you should not write. You must not write this complement. Okay, then you are going to apply. You are going to take the double complement if they are given this expression, and you are going to solve that one. Okay, the option B will be the correct one for this expression. Moving further, the number of 2 to 4 decoders required to implement 4 to 16 decoder. So you know that the first 2 outputs from 0 to 15, there will be 16 outputs, and 0 to 3 there will be a 4. There will be a four inputs. So you need to represent this thing by using 2 to 4 decoders. It is a direct question, and you must know how many decoders, 2 to 4 decoders should required in order to implement 4 to 16 decoder. For that, you know that I need to, in order to get, I have 4 inputs here. I have 4 outputs by using 2 to 4. 2 to 4 decoder has 2 inputs and 4 outputs. Okay, in order to get 16 outputs, okay, it should be 4 into 4. I need 16. I'm going to get 16 outputs. So what I'm going to write, I'm going to write the 4 2 is to 1, sorry, 4 2 to 4 decoder, 4 2 to 4 decoder. I'm going to get from 0 to 3 here, from 4 to 7 here, from 8 to 11, 8, 9, 10, 11 here, from 12 to 15 here. So this will be the 2 inputs. So in order to activate this this 2 to 4 decoders, I'm going to use another 2 to 4 decoder, which comprises of 2 inputs and it comprises of 4 inputs. What I'm going to do here is I'm going to connect the enable of this 2 to 4 decoder. Okay, here I'm going to connect the enable of this one to here, enable to here, and enable to here. I'm going to short all this terminal. I'm going to call this one as some C. I'm going to call this one as D. I'm going to short this D. I'm going to short this C, and C. Here I'm going to apply A, B here, and there will be enable here. Okay, if it is activate that one. So I need, in order to realize 4:16 decoder, the number of 2 to 4 decoders required will be 5. It will be 5. 1, 2, 3, 4, and 5. Okay, this is the answer. This is a direct question, and you must be in a situation that if they ask this question, you must know directly it is 5. Okay, let us moving further. They have asked this question: identify the output Y. We need to identify the output of the following circuit. So they have given that it is a 4 to 1 multiplexer. Since it is a 4 to 1 multiplexer, you have 2 select lines. They are used variable entered map. So you need to identify this expression. You need to identify this expression. Where here, this I can write that this D naught equal to C here, and D1 equal to C bar, and D2 equal to 1, and D3 will be equal to 0, where A equal to S1 here and B equal to S0. Okay, fine. So first, if I'm going to give 0, 0 here, then I'm getting C here. If I'm going to give 0, 0, I'm getting C here. Okay, this D0 line will be selected. If I'm going to give 0, 1 here, this D1 line will be selected. Okay, for that, what I'm going to do here is, if I'm putting 0, 0, the expression is given by A bar. If I am applying 0, 0, that 0, 0 can be written as, since all the terms which I have given are mean terms, I'm going to write with respect to mean terms form, that is SOP form, A bar and B bar. Here it is C, right? So I'm going to write C. Next, coming to next combination, I'm going to apply 0, 1. 0, 1 means A bar B. This line will be selected. It is not yet right. I'm going to write C bar. Next, coming to next combination, I'm going to apply 1, 0. If I'm going to apply 1, 0, 1, 0 means A B bar into 1. A B bar into 1 is, I'm going to get A B bar. Next, I am applying A B into 0. A B into 0. This is A B into 0. I'm going to get this term as 0. So I am going to get this expression A B bar C plus A bar B C bar plus A B bar will be the expression. Since it is a minimal SOP, this is the minimized SOP expression. In order to get the canonical SOP expression, what I have told in the while solving the previous question, we need to multiply the missing terms. Okay, here there is all terms here, there is all terms here, there is a missing C here, C plus C bar. If you add that one, we're going to get A bar B bar C plus A bar B C bar plus A B bar C plus A B bar C bar. Okay, what is A bar B bar C? A bar B bar C equal to 1. Okay, A bar B bar C bar equal to 2. Next here, A B bar C bar, A B bar C equal to 5, and A B bar C bar equal to 4. 1, 2, 4, 5 will be the output. 1, 2, 4 will is the output of the expression of this expression. Okay, Y. So where is that? 1, 2, 4, 5. 1, 2, 4, 5. Option B will be the correct one. Going further, you need to find the output. Okay, they are given some options, multiple choice options. 2 outputs of the following circuits, A and B. Write the correct combination among the following circuit. We need to write the correct combination from this circuit A and B. Okay, for that, what you are going to do here is, so first thing is just look into the options they have given. A and B represent the sum and carry of a off adder respectively. Since off adder has only 2 inputs, here there is a 3 inputs, we can eliminate this option. Next, coming to here, A and B represents sum and carry of the full adder. You need to check this one. Next, A and B represents carry and sum of the full adder. The one common thing is they are given only for full adder. This is the one thing. Next, A and B represents the carry and sum of the off adder. You can eliminate this option. Okay. Here, coming to these two options, whether A represents sum or B represents the sum, you need to identify whether A represents sum or A represents carry. Okay. So that just you must know the truth table of this full adder. In full adder, the output of sum is equal to the output of the sum will be equal to Okay, once again, sorry, there is a technical issue. Moving further, I'm telling that you are going to eliminate directly this off adder and off adder respectively. So in order to, you must know the full adder truth table. Okay, for that, the output of the sum will be, we are going to get this one as 0, 1, 1, 0, that is XOR, and the second part will be 1, 0, 0, it is the XNOT. Coming to carry, here, the carry, here 0, since the output is 0, 0, 0, sorry, 0, 0, 0, 1, and the carry will be 0, 1, 1, 1. If I am going to represent this one in decimal, 0, 1, 2, 3, 4, 5, 6, and 7. Okay, here you can see this is also 0, 1, 2, 3, 4, 5, 6, 7, till 7. So here the sum will be the sum. If I am going to write in summation, the sum will be here 1, 2, 4, and 1, 2, 4, and 7. The sum will be 1, 2, 4, and 7, and the carry will be 3, 5, 6, and 7. So look at the A. A is connected to 3, 5, 6, and 7. 3, 5, 6, 7. So A represents carry here. A represents carry. Look to B. Look into B. Where 1, 2, 4, 7. 1, 2, 4, 7. Okay, it is the sum. So here A will be the A represents the carry. A represents here. A and B represents carry and the sum. A represents the carry and B represents the sum. Option third will be the correct one. Okay, next coming to the problems of comparator. Here, coming to the problem of comparator, here they are given that a 8-bit comparator compares two 8-bit numbers, that is A and B. That means A is 8-bit, A will be 8-bit, and B will be another 8-bit. The number of combinations of zeros and ones, okay, for which A will be less than that of B. That is, A is less than that of B. You need to identify the number of combinations you are going to get for A less than B. So, if you consider that one, there is 8 bits. A represents 8 bits and B represents 8 bits. Therefore, there will be a 16 bit. There will be a 16 bit of input. Okay, if you take 2 power 16, there will be 65,536 combinations of the, you are going to get 65,536 combinations of the input. Where if you take, since it is at 8 bits, so 2 power 8 represents 256, which is equal to A equal to B. You are going to get, for A equal to B, you are going to get 256 combinations. So what we are going to do, we are going to subtract Okay, 256 from this total 65,536. So it will be 256. You are going to subtract that one. You are going to get 0, 8, 2, 65. 65,280. So the remaining here for this combination there will be A not equal to B. For this condition, you are going to get 65,280 combinations. So in that, if you are, it may be A greater than B, or it may be A less than B. Okay, these are the two combinations which leads to A not equal to B. So there is a two combinations. So what you are going to do? Just divide 65,280 by 2. So you are going to get 32,640. This will be the answer. This will be the answer. Okay, this will be for this much combination. A will be less than B, or A will be greater than B. So the answer will be 32,640 combinations for which A is less than B. We are going to write that one. It's a numerical problem. Okay, these are a few problems which I have solved on combinational circuits. Let us move on to sequential circuits. Before that, I'm going to give a brief overview of sequential circuits where the present output depends on the present inputs as well as the past inputs. So it is known as sequential circuit. In sequential circuit, you are going to learn about what do you mean by what is latch, what do you mean by flip flops. These are the concept which comes under sequential circuits. Counters. Before counters, we are going to learn about registers, counters. After that, you are going to learn about some finite state machine based on the given excitation table. You are going to learn about different conversions. These are the things you are going to learn in sequential circuits. Okay. For time being, I am not going to explain what do you mean by what are the different types of latches, flip flops, what are the different types of registers, what are the different types of counters. How we are going to implement that one by that expression by using a finite state machine. I am not dealing with that one directly. I am going to move with the problems. Okay. First, take a simple problem for the JK flip flop with J equal to 1. They are given that J equal to 1 and K equal to 0. The output after clock pulse is. You need to find the output after the clock pulse. So here you must know the truth table of the JK flip flop. If you consider a clock J and K, there is an output here. There will be an output. Suppose there is no we are not applied clock, so I'm going to write this one as 0. So irrespective of the JK out, I'm going to get there is no change in the output. I'm going to get output as it is. If I'm going to apply 1 here, if I'm going to apply 0, 0, then I'm going to get no change. What is the previous output I'm getting? That one will be present here. Next, if I'm going to apply the clock, and if I'm going to apply 0, 1 here, 0, 1, then I'm going to get 0 is reset. Next, if I'm going to apply, I'm going to get 1, 0. Here I'm going to get 1. It is set. This one is reset. This one will be set. Next, if I'm going to apply clock, and in the J equal to 1 and K equal to 1, I'm going to get the toggle. This is going to toggle the previous. If there is 1 in the previous, I'm going to get 0. If the 0 is in the previous, I'm going to get 1. So the question is for J equal to 1, K equal to 0 after applying the clock, J equal to 1, K equal to 0 after applying the clock, what will be the output? So I'm going to get 1. So this one B will be the answer for this one. Next, coming to the second question. A JK flip flop with J equal to 1 and K equal to 1 has 20 kilohertz clock input. So here they have considered a J and K flip flop. There is a clock of 20 kilohertz. They are told that A JK flip flop, that means they have considered only one flip flop. The output will be Q and Q bar. The output will be Q and Q bar. Since they have only one flip flop, they have considered only one flip flop. So there will be two stable states. There will be two states, available states. There will be two states. Okay. So what we are going to do? Just we are going to divide 20 kilohertz divided by 2. We are going to get 10 kilohertz. 10 kilohertz square wave. Since we have two states, I'm going to divide it. I'm going to get the 10 kilohertz. Next, the circuit which changes from serial data to parallel data. So they are given that one circuit the circuit which changes the serial data to parallel data. So in counters, they have not mentioned which counter is this one. Generally, they have mentioned the counters. Where if you consider a multiplexer, so it is impossible. Okay, let us look into other options. Okay, here multiplexer. If you consider a multiplexer has so it is going to convert the parallel data into serial data. These are number of inputs, and it is a 4:1 multiplexer. There's 4 inputs and 1 output. If you consider demultiplexer, it is having 1 input. It is the inversion version of the multiplexer. 1:4. Once you consider 1:4, it will be having 4. So it is going to convert the serial data into parallel data. Okay, it is going to convert the serial data into to a parallel data. So the demultiplexer answer will be the correct answer for this question. Whereas here coming to flip-flop and counters, they are not mentioned which flip-flop they have used or which counter they have used. It is the inappropriate answer for this question. So we are going to choose demultiplexer as the answer. Next, the waveform indicates they are given the waveform, and you need to identify which waveform represents the given options. So here the first thing is here the input is only 1. So input 1 here in JK flip flop, all the things they have considered is positive edge triggering. All the things they have considered is positive edge triggering. In J they have considered JK has 2 inputs, but here there is only 1 bit, so you are going to cancel that option. Okay, that option would not satisfy this question. And coming to this one SR, so it has 2 inputs. Coming to this one, positive edge trigger and positive edge triggering of D flip flop and D flip flop, you must look into the output. So for that one, here there is this is a positive edge trigger, means the circuit will trigger here at the positive edge of the each clock pulses. Okay, fine. Here there is 0 here. Since I am going to look on the D flip flop first, so here you can see that there is 0 here. So when the clock is there is 0 here. I'm going to write as it is. Coming to this clock, the data is 1 here. So data is 1 means I have represented 1 as it is. Coming here, the data is 0 here. So I have represented 0 here. Coming here, the data is 1 here. So here. So it satisfies this thing is satisfying this output. So I am going to represent the option with the D flip flop will be the right one. If you check for D flip flop, okay, it does not satisfy this output. So the option D will be the correct one. So the positive is triggered D flip flop. Just check into this D flip flop. Where in D flip flop, if you give 0, you are going to get the previous state. That means no change. If you give 1, there will be a toggle. For if there is 0 in the past output, it changes to 1. If there is 1, it changes to 0. Okay. Just check into this D flip flop. I'm not going to explain that one. Next, coming to the state transition of D flip flop from 0 to 1 requires. The state transition, in order to transfer D flip flop from 0 to 1, the state required in the D flip flop is. Okay, they asked this question. This is one of the questions they asked in the gate. Okay, where here you know that I'm going to compare the previous and the present. So if you are going to apply 0, think that the previous output is 0. Obviously, the present output will be the 0. Think that if t is equal to 0, think that the previous output is 1, the present output is 1. There is no transition between the previous and present. So if you apply 1 here, if you give that t is equal to 1 here, if the previous data is 1, it's going to toggle right, you are going to get 1 here. If you apply t equal to 1, and if you apply 1, this is going to 1 is toggled to 0. The previous is converted to previous 1 is the present output what you are going to get is 0 here. So according to the question, they asked that T flip flop from 0 to 1 requires. Where the transition is 0 to 1 and the T state is 1. If it is 1, if 1 at T input, the transition will be 0 to 1. From when the T is equal to 1, the transition will be from 0 to 1. So I'm going to choose this option, 1 at T input. So coming to this one, this is also one of the gate questions. They asked that the content of the following registers Q3, Q2, Q1 and Q0 after 3 clock transitions are. Assuming initial values of all the flip-flops are logic 0. So initially I'm going to So first what I'm going to do, I'm going to write Q3, Q2, Q1 and Q0. I need to apply 3 clock pulses. I'm going to apply. So first, before that, there is no clock here. Initially they told that there is 0, 0 here. I'm going to apply 3 clock pulse. What is the output? I'm going to get after that 3 clock pulse that is observed. So if I'm going to apply 0, 0, 0, since this is a data flip-flop or data flip-flop, what will be the output? The output follows the input. The output follows the input. Fine. First, I'm going to get 0, 0, 0 here. If this is a synchronous, where this all clock are started and connected to a single clock. This is synchronous. Okay. Fine. Next, let's move further. So if I'm going to give a clock here, what happens here is 0, 0. If I'm going to give here, there will be a 0 here, there will be a 0 here, since 0 here, 0 here, 0 here. If I'm going to apply clock, what happens is 0 will going to move here, this 0 is going to move here, this 0 is moving here. There is a only moving operation in this first flip-flop, second flip-flop, third flip-flop, and fourth flip-flop. There is a sequence of flip-flops. Okay. Here, let us look into the output of the XOR here. If I'm going to give 0, 0 to the XOR, obviously I'm going to get 0 here. Okay, for first clock, if I'm going to give 0, 0, 0, so I'm going to get 0, 0, 0, 0 here. Suppose if I'm going to give 0, 0, next clock, all these 0, 0 moves here, 0 XOR with 0, I'm going to get, again I'm going to get 0, 0, 0 here. So if I'm going to apply the clock, all 0s moves here, until I get somewhere I need to get 1 in order to become 1 terminal should become 1 here in order to get the XOR output as 1. That combination is impossible in this circuit. Okay, I'm going to get 0, 0, 0, 0. Okay, fine. Until the third clock, fourth clock, fifth clock, I'm going to get 0, 0, 0, 0. For this circuit, for what I'm telling is for this circuit, for the given circuit. Whether it may be if it is XOR or not, just try by using XNOR. For this combination, just try by using XNOR. What happens? Just check it. Okay, we're going to get this is the answer. Next, coming to this example, where when the output Y in the circuit below is 1, it implies that data has changed from 0 to 1 or changed from 1 to 0, changed in either direction, not changed. This is the question they have given. So, here this clock is synchronous. Okay, first I'm going to write the output Y. So before that, they are given this expression. What I am going to do, I am going to call this one as data A, QA bar, DB, QB, Q bar B. This is the expression I am going to call this one, and this will be the clock. Okay, what is the output here? The output is QA ANDed with, this is the AND gate, this one is the AND gate. So QA ANDed with QB. QA is ANDed with QB. Next, here, and again another thing is, you can see that this DB equal to QA bar. You can say that DB equal to QA bar. DB equal to QA bar. Okay, and you can say that since this is a data flip-flop, you can say that this DA equal to QA. Okay, DA equal to QA. So first what I am going to do here is just I am going to write out the table. So I am going to take the block as one input. Okay. Initially I am going to assume the data. I am going to consider the data, and I am going to consider two outputs, that is QA and QB. Let us check QA and QB. So without any clock, so think that I am going to get initially 0, 0. Initially I am going to get initially without any clock, I am getting 0, 0 for simplicity purpose. Next, for the first clock, think that the data is data 1. Think that the data is data 1. So for that one, the QA, since QA is equal to, QA is equal to DA, so what is QA? QA is equal to, I am going to get D1 here. D1. Next, what is DB here? So you can see that DB is equal to QA bar. What is QA bar? So here 0, it will be 1 here. It will be 1. Next, coming to your second block. Next, if you are in second block, if you are thinking that the data is D2. So what is the, since since dA equal to QA, since dA is equal to QA, we are going to get same D2 here. So next, dB is equal to QA bar. dB is equal to QA bar. So QA bar means here D1 bar. Here it will be D1 bar. It will be D1 bar. Okay, you can say that let us generalize this equation. Let us generalize. So if you generalize this equation, you can say that the y is equal to QA into QB, which is equal to the present data, since this QA, whatever we get in the present, is follows, and the past and the previous data's complement. The complement of the previous data, whatever you are getting here. Present data and the complement of the previous data. Okay, here they are told that the y equal to 1. They are told that y equal to 1. Okay, here the output should be 1 here. So if I consider that in order to be 1, I'm going to write this one as 1. The output of the NAND gate is whenever both the inputs are 1, I'm going to get 1. Whenever both the inputs are 1, I'm going to get 1. So in order to get 1, the QA and QB should be equal to 1. So the present data is 1, and in order to be this previous data to be 1, I'm going to take 0 here. 0 it will be complemented. So I'm going to get 1. Complement of 0 is 1, and I'm going to get 1. So it is true. So there is a transition. The previous data what I am taking is here is 0. There is a transition of 0 to the present data 1. Okay, there is a change in the previous data. The previous data is 0, and the present data is 1. There is a transition of 0 to 1. So there is a change. It is the change from 0 to, they are going to change the previous data. The present data, the previous data is changing from 0 to 1. The first option will be the right for this question. Okay. Going further, they have considered the output of the two flip-flops. The output of the two flip-flops Q1 and Q2 in the figure shows are initialized to 0, 0. Okay. The sequence generated at Q1 upon application of the clock signal is, they are given these options. Okay, you need to check that one. So what I am going to do this one is, so first I am going to consider a truth table where it comprises of the present state. Before that, what I am going to do, you can see that this J1 is equal to, J1 is connected to Q2 bar. I am going to write this one. J1 will be equal to Q2 bar. J1 equal to Q2 bar. Next, after that, K1 is equal to Q2. K1 equal to Q2. Okay, fine. Next, after that, J2 equal to, you can see that this is equal to Q1. What is K2? K2 is equal to Q1 bar. Okay. Next, this is the present state of, I'm going to write the state characteristics table where the present state is, I'm going to consider Q1 and Q2. The present state of the Q1 and Q2, they have given that this 0 and 0. Okay, initially there is 0, 0. Okay, let us take the value. The present input for this one will be J1, K1, J2, this will be the present input. Okay. Then the present input. Let us check the next output. Next output will be Q1 plus and Q2 plus will be the next output. So for first combination, okay, here Q1 equal to, they are given that Q1 equal to 0, Q2 equal to 0. Okay. If Q1 equal to 0 and Q2 equal to 0, check what is J1. Since J1 is equal to Q2 bar, look at here. Since J1 is equal to Q2 bar, obviously I'm going to get 1 here. Since Q2 is equal to 0, since K1 is equal to 0, I'm going to get 0 here. Next J2, look at J2. J2 is equal to Q1. What is Q1? Q1 is equal to 0. What is K2? K2 equal to, you can look here, K2 is equal to Q1 bar. We're going to write 1 here. So if you give 1 0 1 0 for first JK flip flop, this is first and this is second. For first JK flip flop, we give 1 0 and if you apply the clock here, okay, for both the flip 1 and 0 1 leads to Q2 is equal to 0 here. Equal to 0. Next, what you are going to do here is next. So 0 here. So this is the next output. It will be the input for the next combination. So I'm going to write 1 0. I'm going to take 1 0. Next, look into the, if you apply 1 0 here, what will be the J1? So since J1 is equal to Q2 bar, I'm going to get here 1. I'm going to write 1. I'm going to get 1. Next K1 is equal to Q2. I'm going to write 0. J2 equal to Q1. I'm going to write 1. And K2 is equal to Q1 bar. I'm going to write 0 here. So J1 is equal to Q2 bar. I'm going to write 1 here. So next, if you apply this one, you are going to get 1 1. Since you have J, the replicable of the J equal to 1, K equal to 1, K equal to 0, you are going to get 1. J2 equal to 1, K2 equal to 0, you are going to get 1 0. So this will be the input to the next combination 1 1. Next, if you apply 1 1 here, if you apply 1 1, so 1 1, since J1 equal to Q2 bar equal to 0, K1 equal to Q2, we're going to get 1, J2 equal to Q1, we're going to get 1, and K2 equal to Q1 bar, we're going to write 0 here. This is 1. So if you apply 1 0, if you apply 0 1 here, it will be 0 here. If you apply 1 0, it will be 1 here. Fine. Next, you are going to take the another combination, that is going to write 0 1 here. 0 1 will be the next combination. 0 1, sorry for that one, is 0 1. So please make a note, this is 0 and this is 1. Since this is the actual combination, this is the present input state now. So if it is 0 1, J1 is equal to Q2 bar, that is 0. K1 is equal to Q2, I'm going to get 1. And J2 equal to Q1, 0. And K2 is equal to Q1 bar equal to 1. So if you take this one, J2 equal to Q1, it is 0. So if you take that one, what you are going to get? If you apply 0 1 here, you are going to get. If you apply 0 1 here, you are going to get 0. Okay, if you apply 0 1 here, you are going to get 0. So you got 0 0. Where you have considered initially you have considered 0 0 here. Finally you got 0 0. If you consider 0 0 and if you do the next combination, you are going to get next state as 1 0 here. So you are done till the next block. So just they ask that the sequence generated at the Q1 upon application of the clock is. They have told that the only the value of Q1 here after applying the clock here. So the combination will be 0 1 1 0 and it continues 0 1 1 0 and it continues 0 1 1 0 0 1 1 0. It continues so on. So the options will be 0. This one 0 1 1 0 0 1 it continues so on. The option D will be the correct one for this question. Okay. Next, moving to another question. I need to find the duty cycle. I need to find the duty cycle of this question. So for that, they are given the T latch. So they are told that 50% duty cycle. That means T on equal to T off. That means the on period equals to T on equal to T off. So here clock 2. So you need to find what you are going to find is you need to find the duty cycle. So you must know what is the formula for duty cycle. The formula for duty cycle is T on divided by T on plus T off. T off. Okay, this T clock divided by 5 represents the delay. This part represents the delay. Where Q2 will be the clock, actual clock, and Q1 will be the data which you have given. So in order to analyze that one, I'm going to discuss this one. Okay, in order to analyze this one, Okay, first I will consider the clock here. First I will consider the clock here. So this is the clock and this one is the data. Okay, you can see that there is a delay here. The delay, I'm going to call this minus t clock divided by 5. So next I'm going to write the output here. Next I'm writing the output. You can see that the output of the clock according to this clock. So here, so since they are told that this is a latch, so it is operated on the positive edge. So on the positive edge. So high level triggering, I'm going to call this one as high level triggering. Okay, here the data is 1 here. Here the data is 1 at this clock pulse. So I'm going to write 1 here. Next here at this part, the data is 0 here. So I'm going to write 0 here. So here until the next high level triggering, I'm going to get the previous state. Here next, here the data input is 1 and the high is there is high. So I'm going to write high till here. Then the data is 0. I'm going to write 0 here until the next clock. I'm going to pass the previous according to the table of the input. I'm going to pass the actual data. Okay. Next here the d is equal to 1. Sorry, the clock is high and d is equal to 1. I'm going to get it till here and again it is 0. So if you consider that one, this will be the t on period. This will be the t on period. Okay. So since they are told that it is a 50% duty cycle, they have in the question they are told that 50% duty cycle. Okay. And they are told that the clock is 1/5 period delay. I have told that 1/5 period delay. You have mentioned that one. The duty cycle at the output of the latch in percentages. You need to tell the output. You need to tell the delay in the output. You need to tell the delay in the output. For that one, this t on, according to this one, this t on equal to, you can say that t clock divided by 2, you're going to minus this one, t clock divided by 5. So if you apply that one, you are going to get 0.3. If you do that calculation, you are going to get t CLK. This is the t on period. So if you write the duty cycle formula, that is 0.3 t clock divided by the t on plus t of this total clock. This is t clock cancels 0.3. If you multiply with 100, you are going to get 30%. So there is a 30% duty. There is a percentage delay. There is 30% delay in the output. Okay, fine. Next, moving further. Problem. Okay. Where they have considered identify the outputs. We need to identify the outputs of the following circuits after the 5 clock transition. The initial values of the flip-flops are, they have asked this one. So you can see that is a synchronous counter, where the clock is output, or ripple counter where the output is connected to the other clock, the output is connected to the other clock, the output is connected to other clock. So next, what we are going to do here is first they are told that we are going to assume 0. I'm going to assume consider Q3, Q2, Q1, and Q0 equal to 0, 0, 0. So without, I'm going to assume that one. So you need to tell the transition after 5 clock pulse. You need to tell the transition after 5 clock pulse. I'm going to tell the analogy how we are going to do that one. So for that, what you are going to do is, since it is connected, since initially this Q is equal to 0, Q1 is equal to 0, and Q3 equal to 0, and Q3 is equal to 0, the output is connected to the other clock. First, if you are going to apply the clock here, so here what happens here, this Q bar equal to, since Q not equal to 0 here, what is Q bar? Q bar equal to 1. Here there is a 1 here. If you apply clock here, what happens is this data will move here. This data. So whatever going to, the Q0 will become 1. Q0 will become 1. Q0 will become 1. And if you apply here 0, here it follows 0 here. Q1 should be equal to 0. Q2 is 0, and Q3 will be 0. Next, what happens is, the same data, if it is 1 now, the here Q bar equal to 0 here, Q bar equal to 0 here. So next what happens is, okay, next if you apply another clock, the input to this one will be 0 here, the input to here is 0. If you apply that one, if you apply another clock, the output is the output of Q naught is 0, and Q bar will become 1. That 1, if that 1 will activate this one, okay, since it is connected to 0 here, it is 1 here. So the output of this one, Q1 will be 1 for the next clock. For the next clock, that output of Q1 is equal to 1. Similarly, if you analyze that one, for the next clock, what happens is, okay, here for both the combination, for Q1 and Q2, you are going to get 1. For Q1 and Q2, you are going to get 1, and the remaining terms will be 0. So we are going to write 0, 1, 1, 0. Okay. Coming to the next clock, we are going to get Q3 equal to 1, and the remaining terms will be 0, 0, 0. Okay. This one will be, sorry, this one is 0, 1, 1. That means both this one will get, I'm going to get 1, and this one will be 0 here. Next, for the next one, so this will be, here I'm going to get, here I'm going to get 0. Here I am going to get 1, here I am going to get 0 here. For the next clock, what I am going to get is, next clock, both the come. It is a counter, it is a counter, 1, 0, 0, 1. You saw this example, it is a similar one. Okay, so I am not explaining in detail, just I have told the analogy of how we are going to solve that one. Okay, we are going to get 1, 0, 0, 1. Okay, this is the, we are going to select this A as the answer. Okay, coming to the next one. The semiconductor memories and computer organization will be explained by Professor Kiran. What do you say? Yes.
Very good evening to all of you. So myself Kiran, Assistant Professor, Department of ECE, Vidyavarada College of Engineering. So now we have to just give a brief overview of a computer organization subject. Before going to solve a previous year gate question papers, let me explain some basic concepts with respect to the computer organization. Here, this diagram shows the functional block diagram of a computer. It mainly consists of a processor, input-output systems, and followed by the memory. As we know that whenever you want to execute any program, generally program is nothing but it is a collection of instructions that are generally stored in a memory. So when you want to execute any program, first you have to fetch the instruction from the memory. Mainly, whenever you are executing any instruction, it mainly consists of 3 steps. So, the first step is the fetching. So first step is the fetching. So fetching is nothing but we have to take the instruction from the memory. The second step is the decoding. So decoding is nothing but we have to identify so what type of operation that computer wants to execute. And once the decoding is performed, the last step is that is execution. So these are the three phases or three stages involved in executing any instructions. And mainly you can observe that the processor mainly consists of a ALU unit and a control unit. As we know that in order to perform a variety of arithmetic and logical operations, the ALU unit plays a very important role that will perform a lot of arithmetic operations like addition, subtraction, multiplication, division, and then logical operations like logical AND, logical OR, logical NOT, different kinds of logical operations. And the control unit, which controls all the operations performed by the ALU by providing the number of clock cycles. So next, here this diagram shows the data path and a control path, because whenever we fetching the data or instruction from the memory, there will be different steps involved in fetching the data or instruction from the memory. That you can observe in this diagram. This is your data memory where we can store the program. That means that both the instructions and as well as the data. Then when you want to fetch these instructions, first you have to know the address from where you have to fetch the instruction. So by providing the address, that program, that is what we call as a program that will fetch the instruction, then that instruction is stored into the register. This is a register. Register is nothing but we can say it is a storage element that will store the either instruction or a data. There are different types, number of registers that is stored in the register bank. Then that instruction later performs a decoding operation in order to identify which type of operation needed to perform. Then that operation is performed by the ALU and produce the result. That result then stored into the memory. Here, this diagram shows how the connections between the processor and the memory. Because as you know that the program is mainly stored in a memory. So whenever processor wants to execute the program, obviously we need to fetch the program from the memory. Here, this diagram shows the interfacing between the memory and the processor. Now you can observe that in the processor there will be different kinds of registers. The first one is the MAR. So MAR means memory address register. So this memory address register basically is a register that will show the address of the memory where you want to fetch the instruction. That is a MAR, memory address register. The next one is the MDR. Here MDR stands for memory data register. So as the name indicates, memory data register. So this register will store the data which is fetched from the memory. And then another register, it is called PC. Here PC stands for, it is a program counter. So generally this PC holds the address of the next instruction to be executed from the memory. Means when the processor is executing the current instruction, the PC that will always show the address of the next instruction to be executed from the memory. That is the PC. It stands for program counter. So next is the another register. It is called IR. IR stands for instruction register. Because when you fetch the instruction from the memory, so that instruction we should store it into the register. That register what we call as instruction register. IR that will hold the instruction. And then there will be different sets of registers which are used for the general purpose, like for the various arithmetic and logical operations. Obviously, we need to hold the data for the operation. For that, there will be a different set of registers which is varying from R0, R1, etc. That is R-1. Then the next unit is nothing but ALU unit. We know that will perform various arithmetic and logical operations. But what are the steps involved when the processor executing the program? Here, when the processor wants to execute the program which is stored in the memory, the first step is the program counter should be set to the point to the first instruction. As you know that the PC always stores the address. Therefore, the first step, the PC should be set to the point of the first instruction where you want to execute your program. Then the content of the PC then transferred to the MER. MER means that is the memory address register, which obviously contains the address of the memory. Then, so in order to read the instruction from the memory along with the PC and the MER, you need to send some control signals like a read signal and also write signal. Here we are reading the instruction from the memory. That's why you have to send the read signal to the memory. Then once you send the read signal to the memory, obviously that will perform a read operation. That means that the first instruction should be read out and which should be loaded into the MDR register. Here MDR means it is a memory data register, which either contains a instruction or a data. Then the content of the MDR are transferred to the IR. IR is the instruction register which is present in the processor. Then you have to perform a decoding operation. Decoding means you have to identify what type of a action required to perform. Then later that will execute the instruction. So next is the instruction format. Basically, 4 types of instruction formats. The first one is the 3 address instructions. Here in a 3 address instruction, general format is we consider any instruction format which mainly consists of a opcode, then operand 1, operand 2, and for example operand 3, because it is in the case of a 3 address instruction. So when you consider instruction format, it mainly consists of a opcode, then followed by the operands. Yeah. What is opcode? So opcode means basically it's an operational code. So that will indicate what type of operation we need to perform. Like opcodes like ADD, that is we have to perform addition operation, or a SUB, that is a subtraction operation. So opcode that indicates what operation we need to perform on the operands. Here operands means which holds the information which is needed to the opcode. Means this opcode either that will holds the data or a part of the data or the address of the data. Yeah, because it is a 3 address instruction, it mainly consists of 3 operands. In that 3 operands, the operand 1, which is acts like a destination operand. Destination operand. Then operand 2 and operand 3 acts like a source operands. So if you can say 3 address instruction example, add R1, R2, R3. In this example, the register R1 which is acts like a destination register, and R2, R3 registers acts like a source registers. Here we have to perform an addition operation. Therefore, R1 is nothing but R1 is equal to R2 plus R3. Then when we consider a 2 address instructions, in a 2 address instructions, it mainly consists of 2 operands. 3 address instruction means it contains 3 operands. A 2 address instruction means it contains 2 operands. Here add R1, R2. So add R1, R2 means here R1 represents your destination operand and R2 represents your source operand. When you consider 2 operand instruction, what will happen means after you perform any arithmetical logical operations, the destination content gets updated. Initially, the destination content contains the one of the data required for the operation, but after you execute the 2 address instruction, the same destination gets updated with the result. Here you can observe the equation that is R1 is equal to R1 is equal to R1 plus R2. So initially R1 contains the one of the data, but after you execute the instruction, the sum of these two numbers result is updated in R1 register. That is a two address instruction which contains two operands. Then the next type is it is a one address instruction. Here in a one address instruction, only you have to mention a one operand. But obviously, when you want to perform any arithmetical or logical operations, we need two operands. But in a one address instruction, what will happen? The other operand, which is a default operand, that should be considered as an accumulator. Here AC stands for accumulator. For the one address instruction, the destination operand is the default is always we should use it as a accumulator as the destination address that we need not to mention in the instruction. That is a one address instruction. Here, for example, add m, where m stands for, we can say it is a variable that will contain some data. So therefore, when we say add m, that means that another operand that should be default, it is a AC, this is the accumulator register. Therefore, AC is equal to AC plus whatever data available in that memory or a variable that should be added, and the result is updated in the accumulator register. Next, the fourth case is it is a zero address instruction. So as the name indicates, zero address instruction means we need not to mention any operands like a operand 1, operand 2. It is like a zero operand instruction, but with a default, this zero address instruction generally uses a stack memory. Stack memory in order to perform a different arithmetical and logical operations. As we know that a stack is a temporary memory where we can store the data by using a instruction push instruction. Whenever we use the push instruction, data is always stored in the stack memory. So when you want to retrieve the data from the stack memory, we have to use the pop operation. Therefore, push and pop instructions are always used with the stack memory. Here when we consider zero address instruction, as we know that internally that will use the stack memory to stores the data and also to perform a variety of arithmetic operations. For that, we have to use the TOS. Here, TOS stands for it is the top of the stack. So when you want to perform an addition operation, obviously we need two operands or two data. So that one of the data stored in TOS, top of the stack, and the second data that should be stored in top of the stack minus 1. So means below the top of the stack memory. And after performs the addition operation, the result is updated to the top of the stack memory. Here is a simple instruction format which mainly consists of an output and followed by the operands. So the next concept is that is addressing modes. Here it is a very important addressing modes that will always describe how we are going to provide the operands in the instruction. That will give the information about how we are going to access or fetch the data from the memory. There are different types of addressing modes. Here this table gives the various types of addressing modes. Here the first one is what we call as the immediate addressing mode. In an immediate addressing mode, what will happen? The instruction itself contains the immediate number or the immediate value. Means the instruction contains the part of the data. Here, for example, if you say move AC move R1 comma hash 50. Here for the immediate addressing mode, the immediate data should be represented by using a hash symbol. So that will gives the immediate number. If we say move R2 comma hash 20, that means that the 20 is the immediate number, that is source operand. That number is generally transferred to the register R2. So if the hash symbol present in the instruction, then we can say that it is the immediate addressing mode. Then the second type is register addressing mode. In a register addressing mode, both destination and the source operand should be a register. Here, for example, add R1 comma R2. So this is an example for the register addressing mode. In this example, you can observe that the source operand and the destination operand both should be a register. So that's why we can call it as a register addressing mode. The next one is the absolute or what we call as a direct addressing mode. In a direct addressing mode, we should mention the address of the data directly in the instruction. Here, for example, add R1, comma 52. Don't confuse with direct addressing mode and also immediate addressing mode. In the immediate addressing mode, we should use the symbol like a hash symbol in order to define an immediate value. But in a direct addressing mode, we simply mention the particular address as a direct number. For example, add R1, comma 52 means 52 means is an address where the data is stored. So that data should be added with the R1 and the result is updated into the register R1. This is a direct addressing mode. So the next one is the indirect addressing mode. So in indirect addressing mode, as the name indicates, we should mention the address in one of the register indirectly. For example, if we say add R1, comma, we should use the parenthesis in order to represent the indirect addressing mode. Here add R1, comma, within the parenthesis R2. That means that the R2 contains the address of the data. Compared to the direct addressing mode, the address of the data which we directly mention in the instruction, but for the indirect addressing mode, where you have to fetch where you have to perform an addition operation or any kind of operation, that data, address of the data, we have stored into the R2, that R2 you have to mention in the instruction, add R1, comma R2. So the next two is the index addressing mode. The index addressing mode, the effective address. Here EA stands for effective address. Is nothing but it is a total address. Effective address should be formed by adding the content of a array. Array means any register content along with the X factor. X represents some constant. For example, if we say add R1, comma 23 within the bracket R2. Here is an example for the index addressing mode. In this type of addressing mode, the effective address, EA stands for effective address, is formed by adding the scaling factor or a constant value. For example, in this case 23 plus whatever the content stored in the R2 register, that is content of R2. So that will give the total effective address where we have to fetch the data. The next is the relative mode addressing mode. So this relative mode addressing mode is with respect to only for fetching the instruction which is in the form of X of PC. So PC means it is a program counter. Therefore, effective address is formed by adding the content of a PC plus the constant value X. Next is the auto increment and auto decrement addressing modes. As the name indicates, auto increment and auto decrement. After you execute that instruction, automatically the particular register will be automatically incremented either to 1, either to 2. That is based on the how many bit operation that we are going to perform, whether it is the 8-bit operation or the 16-bit operation. So now we will discuss some of the gate questions. Here is the first question for computer-based 3-address instruction format. So each address field can be used to specify which of the following. First one, a memory operand or a processor register or a implied accumulative register. Here we know that for the 3-address instruction format, we know 3 operands, operand 1, operand 2 and operand 3. Here operand 1 is nothing but that is your destination operand, and remaining 2 operands that will specify your source operand. Here is the question is how to specify whether these operands either a memory operand or a processor register or a implied accumulator register. As we know that when we consider a destination operand, so destination operand, It can be a memory operand or it can be a processor register. It cannot be a immediate value, because we know that destination is it's the point where we have to store the result. Therefore, we need some memory location, or we can use the register. Therefore, operands should be a memory operand or a processor register. It cannot be a implied accumulated register, because we know that in the case of 3-address instruction, we cannot use the implied accumulated register. That can be used only in the case of the 1-address instruction. Therefore, the address fields are operands. Either it can be a memory operand or it can be a processor register. That is, either it is S1 or it is S2. So next is the second question. Here the second question is, consider a hypothetical processor with the instruction of a type LW R1, at 20 of R2, which during execution that reads a 32-bit word from the memory and stores it in a 32-bit register R1. The effective address of the memory location is obtained by the addition of constant 20 and the content of the register R2. Then which of the following best reflects the addressing mode implemented by this instruction for the operand in memory? Here the given instruction is, it is LW R1, 20 of R2. Here LW means this instruction stands for load a word. Load a word. We have to identify which type of addressing mode it is. LW R1, 20 of R2. If we consider the 4 options, the first option is immediate addressing mode. Obviously, it is not immediate addressing mode, because we know that in immediate addressing mode, the source operand should be mentioned by using a symbol hash. Obviously, this is not immediate addressing mode. And next, the second option is register addressing mode. We know that in a register addressing mode, both destination operand and source operand should be a register. So in this example, we can say that R1 and R2 are the register, but there will be a constant or a scaling factor 20 is present in the instruction. Therefore, it cannot be a register addressing. The next one is a register indirect scaled addressing mode. In a register indirect scaled addressing mode, only you have to use the registers indirectly. For example, this can be written as LW R1. Then within the parenthesis R2. So this instruction, then we can say that it is a register indirect scaled addressing mode, because the R2 register indirectly used to hold the address of the data. So third option also is not correct. Then the last one, base indexed addressing mode. Obviously, you can observe this instruction LW R1, 20 of R2. That means that the effective address is followed by adding the constant value 20 plus the content of R2, right? That is the effective address. Therefore, here we are adding a constant 20 to the content of the R2. So, this is an example for the index addressing mode, or what we call as a base indexed addressing mode. Therefore, answer for this question is it is base indexed addressing mode, because that uses a constant 20 to form a effective address. So then the next question is, consider a processor with 64 registers. You have to consider a processor with a total number of registers of 64 and the instruction set of size 12. Instruction set of size 12. Each instruction has a 5 distinct fields, namely opcode, 2 source register identifiers, and 1 destination register identifier, and a 12-bit immediate value. Then each instruction must be stored in a memory in a byte-aligned fashion. If a program has 100 instructions, then the amount of memory in terms of bytes consumed by the program text is how much. That we have to calculate what is the total number of memory used for storing the 100 instructions. Here in this example, you can observe that. So there is a processor which consists of a 64 registers. Totally there will be a 64 registers. 64 registers, okay, fine. and an instruction set of a size 12. Here if you observe this particular question, instruction set, there will be instruction set of size 12. That means that there will be instruction set which consists of a 12 instructions. So total number of instructions are 12. Then when we consider each instruction which is having a 5 distinct fields, when we consider an instruction, it has a 5 distinct fields. The first field is, it is called opcode. Opcode is nothing but what is operational code, or we can call it as it is an instruction that will specify what kind of operation we need to perform. That is the opcode. The next is the two source register identifiers. For example, R1 and R2, and one destination register, you can say R3, then followed by a 12-bit immediate value. 12-bit immediate value. So this is the each instruction format. First we have to determine the how many byte or how many bits is required for storing the one instruction. So this is a one instruction format which consists of opcode, then followed by 3 registers, and then followed by the 12-bit immediate value. Here for that, first you have to calculate how many bits are needed to represent the registers. In this example, it consists of 64 registers. So there will be 64 registers. The number of bits used for representing the register is, we should use the formula C log to the base 2, the total number of registers, that is 64. So C means whenever you get a real numbers, that should be round up to the next higher integer. Here the number of bits, that is log 64 to the base 2 is nothing but you will get 6 bits. So 6 bits are used to represent the every register. So therefore, if you want to represent R3, it is 6 bits, R1 6 bits, R2 6 bits, then as usual immediate value is a 12 bit. Okay, next for the opcode. For opcode, how many bits we require? For that, opcode is nothing but it is an instruction. So in this example, the total number of instructions are, it is 12. Okay, there will be a total 12 instructions. So if you want to represent a one instruction, so how many bits required? For that, again, how to use this formula, number of bits used to represent the instruction is, that is the seal symbol, that is a log of a total number of instructions is 12 with a base 2. So when you consider a log 12 with a base 2, you will get 3.25 something. So that should be round up to the higher integer. Then a number of bits required to represent an instruction is, it is a 4 bits. Therefore, opcode field requires 4 bits. Then when we add this total number of bits, it is 4 plus 6 plus 6 plus 6 is equal to 18 plus 12. So we get 34 bits. So 34 bits are required for storing a one instruction. So then we have to calculate how many bytes required for storing 100 instructions. That should be in terms of bytes. First I will convert this 34 bits into the bytes by dividing 2. So we will get 4.2 bytes. Right? So and also they mentioned that each instruction must be stored in a memory in a byte aligned fashion. Here byte aligned fashion means if you consider a memory which consists of memory locations, and every memory location is a byte. That means every memory location can capable of storing so 1 byte information. And now we can observe that we are getting 4.2 bytes. So real numbers we will not consider, that should be round off to the higher integer. 4.2 means you will get a 5 bytes we will consider. Therefore, if you want to store a one instruction, we need 5 bytes. Therefore, if you want to store 100 instructions, then 100 into 5, you will get 500 bytes. So that is the answer. 500 bytes memory required to store a 100 instructions. Okay, next. So the next question is, a machine has a 32-bit architecture with a one-word long instruction. It has 64 registers, so each of which is 32 bits long. It needs to support 45 instructions which have an immediate operand in addition to 2 register operands. Assuming that immediate operand is an unsigned integer, then the maximum value of the immediate operand is. Here in this example, you can observe that totally there will be 64 registers and then 45 instructions. The machine having a 32-bit architecture. That means that every instruction size is a 32-bit. So when you consider instruction format, so it is a 32-bit long. The size of the every instruction is a 32-bit long. So this instruction consists of a opcode, then immediate operand in addition to 2 register operands. There will be 2 registers, R1 say R2. Then in addition to 2 registers, there will be a one immediate value. So now we have to find out what is the maximum value for the immediate operand. So for that we have to calculate the number of bits which is used to represent the immediate value. Here you can observe totally there will be a 32-bit. So in the given question there will be a total number of registers are 64 registers. 64 registers. So now we have to calculate the number of bits to represent every register, that is ceil of log 64 with base 2, you will get 6 bits. 6 bits. Therefore, here R1 we require 6 bits and R2 we require 6 bits. Then it contains 45 instructions. So for 45 instructions, again you have to calculate the number of bits to represent a instruction. So it is log 45 with base 2. C function you have to consider.
The current flow in the particular device, we need to apply the potential
So
difference.
log 45 with base 2 is.
So the corresponding current mechanism is known as the drift current mechanism.
We get approximately
whenever there is a concentration gradient in that particular device,
5.72
the current
something. That should be equal to 6.
And again, we need to understand the mobility and the resistivity in that particular device.
So your opcode also requires 6 bits. So now out of 32 bit, then how much bit required for representing the immediate value is nothing but subtract 32 minus 18. So you will get 14 bit. So that is representing the immediate value, we require 14 bit. So now the question is, so what is the maximum value that we can represents as a immediate value? Because this immediate value is the unsigned integer. So we know that the range for the unsigned integer is it is generally 0 to 2 power n minus 1. So that is the range for the unsigned integer. Here the small letter n stands for the number of bits used to represent the value. Therefore, in this case, the immediate value is 14 bit. Therefore, the range is 0 to 2 power 14 minus 1. So 2 power 14 minus 1 is the maximum value. So you will get 16,383. 16,383. So that is the maximum value of the immediate operand that we can include in the instruction. So let us consider the next question. Here consider a RISC machine where each instruction is exactly the 4 bytes long. Conditional and unconditional branch instructions use PC relative addressing mode with the offset specified in bytes to the target location of the branch instruction. Further, the offset is always with respect to the address of the next instruction in the program sequence. So consider the following instruction sequence. If the target of the branch instruction is I, then the decimal value of the offset is. You have to calculate the decimal value of the offset for the branch instruction. Yeah, this is the simple example program that contains add R2, R3, R4, subtraction R5, R6, R7, then comparison R1, R9, R10, then branch equal R1, offset. And also they mention the instruction numbers. It is I plus 1, I plus 2, and I plus 3. And also in the problem, they mentioned that every instruction is a 4 bytes long. Means if you want to store every instruction in memory, it requires 4 bytes of a memory. 4 bytes of a memory. Then when you consider a memory map, let us say first initial address is I. So for adding for storing the first instruction, it will take 4 bytes. So the next instruction is obviously it is I plus 3. I plus 3. So next instruction also takes a 4 bytes. The next instruction is it is I plus 8. The fourth instruction is it is I plus 12. Then the next instruction is it is I plus 16. I plus 16. Yeah, as we know that whenever the processor executing the current instruction, the PC is always loads the address of the next instruction to be executed. Therefore, whenever the processor executing the last instruction, there is a branch instruction, there is a branch equal R1, offset, then the PC value is always the next instruction, that is I plus 16, right? I plus 16. Whenever this condition is satisfied, what will happen means the branch is shifted to the initial address, that is to the I. So therefore, we have to calculate the what is the value of a offset address. For that, there will be a formula: effective address is equal to PC program counter content plus offset address. After the branch instruction, obviously the program counter is shifted to the first point. So let us say its address is 0, initial address is 0, 0 is equal to the PC address is obviously it is 16 plus offset. But then the offset address, it is minus 16. Therefore, a decimal value of the offset is, it is minus 16. So next question. Consider the following program segment. Here R1, R2, R3 are the general purpose registers. So assume that the content of the memory location is 3000 is 10 and the content of the register R3 is 2000. The content of each of the memory locations from 2000 to 2010 is 100. The program is loaded from the memory location is 1000. All the numbers are in decimal. Assume that memory is a byte addressable and the word size is 32 bits. If an interrupt occurs during the execution of the instruction, that is a increment INC R3, what return address will be pushed onto the stack? We are given the simple program segment, and also they mention the number of words it will take to store in a memory location. Here only I will explain. For example, So this is say your memory locations. Your word size means it is 32 bits, and these memory locations are byte addressable. So byte addressable. And also you mentioned in the question that the program is loaded from the memory location is 1000, means the first address is, it is 1000. It is 1000. So the first instruction is move R1 comma within the parenthesis 3000. It require number of words are 2. So each word is a 32 bit. Then 2 words means you will get 64 bits. So 64 bits means what in terms of bytes? 8 bytes. We require to store a first instruction. We require to store a 8 bytes. So therefore, the next location is 1007. 1008. So for the next instruction, it is move R2 comma R3. It will take one word. One word means 32 bytes. That is, it will take 4 bytes. 108 plus 4. 108 plus 4. The next instruction also takes 4 bytes. Again 4. Next one also 1 word. Next one also 1 word. Next one also 1 word. Next one. So branch instruction, it will take 2 bytes. So 2 bytes means it is 8 bytes. So when you add all these memory locations, so you will get 1024. 1024. At this point, it is 1020. The next one is it is 1024. So whenever branch instruction is executed, as we know that when the processor executing the current instruction, a PC is always loaded with the address of the next instruction. Then whenever interrupt is occur at the branch instruction, what will happen? That will stops the currently executing instruction and pushes the address of the next instruction onto the stack memory. That is 1024. The address 1024, which is pushed into the stack memory. Therefore, the return address will be pushed onto the stack is 1024. So the next question is, a processor has 64 registers and uses 16-bit instruction format. It has 2 types of instructions. One is I type and another one is R type. Each I type instruction contains an opcode, a register name, and a 4-bit immediate value. Each R type instruction contains opcode and a register names. If there are 8 distinct I type opcodes, then the maximum number of distinct R type opcode is. So in this example, again you have to use the concept, that is, it consists of a 64 registers. There will be a 64 registers and uses a 16-bit instruction format. 16-bit instruction format. There will be 2 types of instruction format. One is I type and another one is R type. If you consider I type, it contains opcode, register, then 4-bit immediate value. If you consider R type instruction format, which contains opcode, and then 2 registers, R1 and R2. And length of each register is 16-bit because it uses 16-bit instruction format. 16-bit. So first you have to determine the number of bits required to represent the each instruction. For that, again you have to use the same formula. Number of bits is ceil function log 64 with base 2. You will get 6 bits. 6 bits are required to represent the every register. Therefore, R is equal to 6 bit and there will be a 4-bit immediate value. Therefore, the remaining opcode is 6 bit for the I type. 6 bit for the I type. Similarly, for the R type, R2 is 6 bit and R1 is 6-bit, and remaining is it is a 4-bit for the opcode for the R type. So next we have to calculate what is the maximum number of distinct R type opcodes is. So when calculating the maximum number of distinct R type, we can change the R. There will be 64 registers. By taking the different permutations, you will get a different number of instructions that we will calculate. And in the given problem, they mentioned that there will be a 16-bit instruction format. If it is a 16-bit instruction format, what is the total number of possible instructions are? It is 2 power 16. It's a 16-bit format, means obviously the total number of instructions are 16-bit. So it is nothing but this total number of 16s. Then when you consider I type, so I type is nothing but it is 2 power 6. Right here, I type is 2 power 6 into 2 power 6 into 2 power 4 plus the R type, means we have to calculate the distinct number of opcodes that I will treat it as a X. This 2 power 6 and 2 power 6 is equal to 2 to the power of 16. That is the total number of possible instructions. We have to calculate the X. So this will becomes we have to consider 2 power 6 and 2 power 4. 2 power 12 plus x into 2 power, this is 2 power 16, is 2 power 12 is equal to 2 power 16. When you take an x as a common factor, you will get here 2 power 14 is equal to 2 power 16. Then x is equal to 2 power 16 divided by 2 power 12. We'll get 2 power 14. So therefore x is equal to 16. So that is a maximum number of distinct R type code is, that is a 2 power 4, it is 16. So the next question is, the following are some events that occur after a device controller issues an interrupt while process L is under execution. The first one is the processor pushes the process status of a L onto the control stack. The second one is the processor finishes the execution of the current instruction. Then the next is processor executes the instruction service routine. Then processor pops the processor status of the L from the control stack. And the processor loads the new PC value based on the interrupt. Here, which one of the following is the correct order in which the events above occur? As we know that whenever the instruction occur in the program, the microprocessor that will perform a sequence of actions. As we know that when the microprocessor executing the instruction, so whenever a interrupt is occur, what are all the actions should be takes place by the microprocessor? The first step is the processor should pushes the process status of the L onto the control stack. First we have to push the status of the current register onto the stack memory. So once you pushes the status of the stack memory, the next is we should load the the processor should be, first is the P. The next is the processor loads the new PC value based on the interrupt. So then once the new PC value is loaded, then according to the new PC value, the processor executes the interrupt service routine. That is, first one is P, second order is T, next is R. So once the processor executes the interrupt service routine, the next one is the processor has to come back to the main program where it executes the current instruction. For that, processor pops the process status of the L from the control stack, that is yes. Then processor finish the execution of the current instruction, that is Q. Here this is the order, a correct order that is executed whenever processor is interrupted. That is PTR-SQ. That is a option B. So next, consider the following sequence of a micro operations, that is MDR. This one is MDR, PC, next MAR, X, PCY, memory, MDR. Which one of the following is a possible operation performed by this sequence? We can observe that this micro operations, there will be 4 options. First one is the instruction fetch. So we know that whenever we fetching the instruction, PC, we should load it with the address. Therefore, first option is not correct. The second one is operand fetch. So whenever we fetching the data or the operand, we should use the instruction register. IR register we should use in order to fetch the operand and store it into the register. Therefore, a second option also it is not correct. The next is the conditional branch. Whenever conditional branch is executed, as we know that the PC should be loaded with a new address. But here PC value is loaded to some MDR register. Therefore, option 3 also it is not correct. Then the last option, obviously, it is a initialization of the interrupt service. So that is the answer for this question. That is initialization of the interrupt service. So this will covers the some basic gate level questions with respect to the computer organization. Thank you all.